Hello everyone. Today I'm going to talk to you about a parser for the highest level programming language. That is a parser for natural language. What we're interested in is building virtual assistants that can understand compositional commands. Because compositionality allows for millions of commands and allows for a lot of useful things. And these are some examples that are all supported for our system. So we can have event-driven command, such as when my advisor is online on Slack, send me to away. We can have commands that connect multiple services, such as automatically uploading my Instagram pictures to Twitter. We can have commands that compute, such as computing the total size of all my files in Dropbox. And we can also have access control commands. So my parents can be allowed to see my security camera only under certain conditions. And our tool can build compositional virtual assistants. And the users of this tool don't need any machine learning expertise. And they can be experts in the domain instead. So the standard technique to build compositional virtual assistant is semantic parsing. This is a machine learning algorithm that translates natural language to a formal representation. And so for state-of-the-art virtual assistant, this formal representation is a domain-specific intermediate representation, often in the form of a tree or a graph, where the nodes are associated with words in the input sentence. And then this intermediate representation is sent to an inference engine for actual execution. And this intermediate representation is ill-defined as ad hoc semantics. Every domain must be specified separately against an ontology. And domain in this case means like music, home automation, your phone commands. Each one of those has to be specified separately, and it's expensive to do. And the representation depends heavily on the input syntax. So sentences that could be similar can have different representation. And we propose to cut away all the intermediate stuff and translate directly to what we call is a virtual assistant programming language, or VAPL for short. This is an executable representation that calls into an API, a library of APIs, as well-defined semantics and well-defined operators, and we can execute the code directly. And the way we're going to do it, we're going to use a deep neural network to translate natural language directly into code. And neural networks are powerful, but they need a lot of data. So we introduce a tool, takes the definition of the virtual assistant programming language we care about, takes templates written by domain experts, and automatically generates the training data for the neural network. And so we're going to translate into a programming language. So let's see, we're going to first describe the design of this programming language and how it influences the translation. So our first VAPL that we design is ThingTalk. ThingTalk has a simple construct. It has when with filters, get with filters, and do. When define when the command executes, get define what to do, and do define what data to get, and do define what to do. And each one of those comes from a large API library that defines both the actual API and how you express in natural language. So you can combine a cat picture with post on Facebook, and you get a cat picture and post it on Facebook. And so not all languages are equally good, and because we are translating into a programming language, we get to design this language, and so that we can improve translation. And from our experience with ThingTalk, we have identified 5 principles that improve the quality, and I'm going to go into details of each one. So the first principle is orthogonality in function types. What do I mean by that is, first version of ThingTalk had 3 functions, 3 types of functions corresponding to the 3 clauses in the construct. So you had triggers for events, you had retrievals to read data, and you had actions for side effects. And these are 2 examples of triggers and retrieval. When PLDI tweets is a trigger, and get PLDI tweets is a retrieval. And you can immediately see that they're very similar. It's very easy for a translator to get confused between the two. And if for every API you had both ways, both a trigger and a retrieval, then this would be fine. You could learn the distinction. But if you let developers just write these APIs, you will get a much inconsistent library. So we suggest that you should unify the trigger and retrieval operators. We introduce a monitor operator. We change the design and the implementation of the language, and now the language has uniform semantics. This both improves the usability, because now every command goes both ways, and every command you can monitor, and also improves the translation, because the neural network can learn that tweets is a domain-specific word, is an API-specific word, and when and get are general words. The next principle is that you should use construct that match the user's mental model. So in our domain, we say the users like to think of data with certain characteristics, and so our construct is data-driven. It's a stream, a query, and an action. And here is another example of a ThingTalk program that takes all the tweets coming from PLDI and retweets them. You can see there are no variables. You name the parameter directly. There are no loops. You directly iterate the result if the API returns multiple results. And there are no if statements, and because they're replaced by filters. And this matches the fact that you wouldn't have those in natural language. The next principle is that you should have strong static typing to guide generation towards meaningful program, that is, weed out all programs that really don't make sense. We propose rich type systems with domain-specific types. In our case, that would be pictures, locations, date. Even hashtags should be their own type. We also notice that you need a rich constant language. For example, you need the ability to specify compound measures, because if the user says 6 feet 2 inches in the sentence, you cannot do arithmetic during translation to normalize that. You also need relative dates and relative locations, because you want to translate without respect to a specific time or a specific user. We get to design the syntax, and we get to make small syntax tricks to improve translation. One that we have found very effective is to use keyword parameters, because parameters are often unspecified, and with keywords we don't need to learn a lot of placeholders. And the last principle is canonicalization. So we say that a programming language is canonicalizable if for every semantics there exists a unique syntactic form up to functions in the library. And so this is an example of a canonicalization step. We take all the filters predicates and we reorder them in alphabetical order according to the parameter name. Canonicalization is necessary to evaluate if the program is correct, because we need to evaluate statically. We cannot run the program if it has side effects. It is also necessary to train, because the standard sequence-to-sequence training strategy is word-level loss. We match word by word the training set and the program we generate. And in fact, because this is the training strategy, canonicalization has a 4 to 7% effect in accuracy. So now that we have defined a virtual assistant programming language, how do we go and build a semantic parser? So what is hard about semantic parser? In a way, and a lot like all machine learning, it's all about data. In fact, we need a lot of annotated data to train the neural network. In a semantic parser, annotated data means pairs of sentences and programs. And writing programs is hard. You need an expert who understands a programming language. You need a programmer. So annotations done by hand are very expensive. But our tool can generate high-quality annotated training data with minimal amount of human effort. So why is it hard to annotate? Well, we know that the same function can be used in many different ways. So the same list folder function from Dropbox can be used to list the files in Dropbox, can be used to notify when you modify a file, because you report the modification time, can be used to notify when you create a file. And that means the state-of-the-art technique that based on a single canonical form for each API are not sufficient. We let developers write all the different ways the APIs can be invoked. It's also notable that the same API can be both a noun and a verb, so it will have different places in the English sentence where the API is used. And the next thing to observe is that even the way APIs get combined has a lot of variety. The same get a cat picture and post on Facebook can be said in a lot of different ways. And so pipeline, we started by having API developers and experts in the API provide primitive templates specifying how the APIs get invoked. These are combined with the definition of the language and the construct. Each construct is associated with a grammar or natural language that defines how the corresponding natural language gets combined to form sentences. So you can have the when something, then do something, or do something, when something, and they go into the same program. Out of these two, we just synthesize a large space of a large training set. A subset of that will be paraphrased by crowdsourced workers, and both paraphrase data and synthesized data will be combined with existing corporas or names and songs and even free-form text in an augmentation step to create the training data. And note that we train with both synthesized and paraphrase data, unlike previous work. Synthesized data provides compositionality because it sees all the possible combinations of different APIs, whereas paraphrase data will take a single command and write a lot of different varieties, so it provides robustness. In fact, paraphrases, very few paraphrases are novel, but we can, or introduce a new syntactic form, but we can boost by observing interesting paraphrases, writing new construct templates, and then those construct templates will go into the synthesized data and improve the quality. Machine learning model is an off-the-shelf model called DECNLP. It's a contextual question answering model. So it's an encoder-decoder network with both BILSTM and self-attention. We have modified it for semantic parsing by adding a pre-trained network, a pre-trained layer. We take advantage of the fact we can generate a large space of programs automatically and pre-train the decoder. So moving on to experimental results, the first thing to observe is that we'll have different data for different purposes. We are using our tool, we generate 1.3 million synthesized sentences, for which we sample 24,000 paraphrases. This turns out to be about $8,000 on Amazon Mechanical Turk. And after augmentation, our training set is 3.6 millions. Given our training set, our next concern is evaluation. And we cannot evaluate on synthesized data because that's algorithmically generated, it's not meaningful. State of the art is to evaluate on paraphrases, but paraphrases are also misleading. You can get very high accuracy on paraphrases and still do very poor when you deploy your system in the real world. So we propose to evaluate on a small set of realistic user data. We acquire this in two ways. The cheat sheet method consists of writing a cheat sheet of all the different things the system supports. We show it to a Mechanical Turk worker. Then we take the cheat sheet away and we ask for a compound command, and we annotate that. And the other form is just use IFTTT data. We take the commands that we support. These are commands that are written by people who have nothing to do with our system, and therefore are the most representative of real sentences. We collect about 1,500 sentences for validation, and we use this to refine the templates and improve our accuracy, write more primitive templates until we get good results. And the test set gives us final accuracy number. And the takeaway is that Genie improves the state of the art significantly. Up from a 20% we had before, we get to 62%. And we know that we had no real data in our training, but we already get 62% on real data. And we didn't have any domain-specific effort. We worked just on compositionality. And also note that previous work on IFTTT only got 3%. And we experimented training with both synthesized and paraphrase data, and we find that the role of the data is complementary, so you should train with both. And finally, we have applied Genie beyond just ThingTalk. We have applied it to a domain with a single Spotify skill supporting compound commands. And we show that if you put effort in a specific domain, you can boost your accuracy all the way to 80%, even on compound commands. We have applied it to a language for access control on primitives, and we get good results on that too. And also we applied to an extension of ThingTalk where we get similar results as around 60% accuracy. And to recap, our approach is to take user input natural language, translate it directly to executable code, and we have shown the Genie tool that takes the definition of the programming language, takes templates written by domain experts, and a large corpus of existing parameters, and generates the semantic parser. We have shown that Genie works in different domains and different programming languages. It is cheap, and you can use it without any machine learning expertise. And it is now part of LuiNet, our open source model for linguistic UIs. Thank you.
We have time for questions.
This was cool work. Do you see opportunities to move from an off-the-shelf model to something that's more designed? Since you have a lot of structure here, you have a lot of program structure, the structure of the programs. Have you guys thought about that?
We did.
Yeah.
So we did some experiments on the different decoder architectures.
Yeah.
We found that until you go into like really pushing the compositionality, like zero-shot compositionality, it's really hard to find that there is any difference.
Yep.
Partly because the language itself is designed so it aligns well with the input.
Yeah.
So
Cool. All right. Thanks.
More questions? Okay, that concludes the session. Thank you.
thank you.